Hi everyone, and welcome to another seminar of mathematics and high energy physics at Physics Latam. Today we are happy to have Dr. Chien-Yeah Seng. Currently, he's a researcher at the University of Washington. Chien-Yeah obtained his PhD at the University of Massachusetts, Amherst, in 2016 under the supervision of Professor Michael Jeffrey Ramsey Mussel, following two postdocs position, one at Shanghai Jiaotong University and the other one at Bonn University, where I was lucky to work with him and learn a lot of QFT and QCD thanks to him. His expertise areas include nuclear decays, standard model, beyond standard model, nuclear beta decays, radiative corrections, among many others. In recent years, he has been able to theoretically predict and update several parameters within the standard model, just to mention some, new corrections to the super allow nuclear beta decay, CKN matrix unitarity, radiative correction to KL3 decays, and the BUS and BUD updates, and so on. With this new data, pushing forward the latest prediction test of the standard model. So we are very happy to have him with us today. I hope you enjoy this seminar about chiral perturbation theory, and now I leave you all with him.
Yeah, thanks, Daniel, for the very kind invitation to allow me to give a talk of about 2 hours and introduce to you some of the basic concepts in chiral perturbation theory. So chiral perturbation theory is a low energy effective theory of hadrons, which is now the foundation for the studies of properties and interactions of nuclei using ab initio many-body methods. So as you can easily imagine, it's impossible to give you a very complete lecture of this topic within 2 hours. It can easily take up a semester or two to cover all the aspects. But my hope is that this talk will introduce to you some basic concepts and key formula, and then you can easily rewatch the video anytime you like. So, and it's very natural that because this the theory itself is quite mathematically inclined. So at the middle or even before the middle, you will stop following what I'm talking about. But the video is there and the key formula is there. So when you are interested, you can look back and then go to the more detailed reference and find out the derivation. So this is the hope. Okay. So now let me switch my slide. Okay, now here's the outline. I have a lot of sections, as you may be scared by this many sections, but don't be worried. Many of them are just a few slides, well, very short. So I will introduce a strong interaction and explain why it's very difficult to deal with it at low energy, and introduce the concept of effective field theory. And then we want to build an effective field theory based on the symmetries of QCD and in particular the spontaneously broken chiral symmetry, which I will explain. And then we'll introduce the so-called Nambu-Goldstone boson, which is generated from the spontaneously broken symmetry, which is the ingredients of chiral perturbation theory. And then I will write down the lowest order Lagrangian for the Nambu-Goldstone boson and the nucleons. And then calculate several observables for an example. So as a prerequisite to understand this talk, you may need some basic knowledge of quantum mechanics, quantum field theory, and group theory, which I think you have previous lectures, online lectures on QFT. So I think most of them do have this basic knowledge. And then there are several useful textbooks for chiral perturbation theory. So this one I particularly recommend is a primer for chiral perturbation theory written by Scherer and Schindler, which is one of the standard texts to study chiral perturbation theory. And I also recommend the Dynamics of the Standard Model written by Donahue, Golovich, and Holstein. Although this book is not just about chiral perturbation theory, but it has a few sections about it in the section of effective field theory, which explains several key concepts related to chiral perturbation theory very well. Okay, so without further delay, let's get started. So as you may know, there are four forces or four fundamental forces in the universe, namely the strong interaction that binds protons and neutrons to form nuclei, and electromagnetism. So you have electric force and magnetic force. And then you have weak interactions, for example, those that govern the beta decays. And finally, you have gravity, that every two massive objects will attract each other. And then these four forces have a hierarchy in terms of its strength. And as you know very well, that the strong force, if you normalize the strength of the strong force to 1, then the electromagnetic force is like 2 orders of magnitude smaller. The weak force is 7 order of magnitude, and gravity is 38 order of magnitude smaller. So this is by computing the force between two protons confined in the nucleus, which radius is around is of the scale 1 over m pi. So many of them are, so many of I mean, so the strength of the force is governed by two factors basically. First is of course the coupling constant, and the second is the force transmitter. So for instance, the electromagnetic coupling is weak because this coupling constant, we call it the fine structure constant. Alpha is like 1 over 137, which is relatively small, while the weak force is much smaller because it's the force transmitter is a heavy boson. So the W boson and Z boson, which is very massive, so its propagator has a mass suppression. And the gravity, of course, is coupling constant is even much smaller. So today we are talking mainly about the strong force that binds hadrons, binds protons and neutrons to form nuclei. And to introduce the term, we call the observed particles that take place in the strong interactions as hadrons. So in general, we classify the hadrons into two types: the mesons, which are hadrons with integer spin, namely they are bosons, and the baryons, which are hadrons with half integer spin, namely they are fermions. So the well-known pion, kaons, and eta, for instance, falls into the category of mesons, whereas the proton and neutrons are baryons. So now, unlike leptons such as electron, muon, and tauon, there are only a few of them. We have found a lot of hadrons, many tens and hundreds of them. And then, so it was in the early days in the study of strong interaction, it was a whole mess. So we don't understand why there are so many hadrons and what is the fundamental theory of the strong interaction. So this is a very, very sketchy and very rough history of the evolution of the strong interaction picture. So in 1935, Yukawa proposed that the protons and neutron the proton and neutron interact by exchange of a pion. And then a few decades after that, Gell-Mann and Zweig, by observing the hadron spectrum, found some pattern of the hadron spectrum, namely that the several hadron group into form groups which are similar properties. So they propose that hadrons are not elementary particles, but composite particles built up by more smaller elements known as quark. So they introduced a quark model. And by trying to figure out how quark interacts, people then introduced the concept of color, namely each quark has 3 choices of color, and then the quarks interacts by transmitting color force. That leads to the formation the construction of the quantum chromodynamics, or QCD, which is now the fundamental theory of strong interaction. So now the quark model built by Gelman and Zweig suggested that hadrons are not elementary particle, but made up of smaller constituents known as quarks. So in this model, mesons are formed by a quark and an antiquark, while the baryon is formed by three quarks. So you can see, you may be very familiar with this. A proton is up, up, down, and neutron is up, down, down, and pi plus is UD bar, pi minus is DU bar, and so on. But so this is a very simple picture which suggests that there are only three quarks in the baryon and two quarks in the mesons. But of course, nowadays our understanding has improved, and we know that this is not a complete picture. So this constituent quark picture is heavily incomplete, and in fact, we have infinite many quarks and in a hadron. So apart from the three constituent quarks in the baryon, you may have C quark pairs, so a lot of them. And now the next question is obviously, if we have quarks, then how do they interact with each other? Sorry, just give me a second. Okay, yep. So now, as we mentioned before, that people have figured out that the quark carry color, and then they interact by emitting some color carrying force carrier known as gluon. So that form the basics of the so-called quantum chromodynamics, which says that the hadrons are formed by quarks. Formed up by quarks. So there are six flavors of quark. Up, down, strange are the lightest one, and the charm, bottom, top are the more heavier ones. And then by exchanging the so-called gluons, they will interact with each other. So this is the basic Lagrangian of the QCD, quantum chromodynamics, which is now the standard fundamental theory of strong interaction. So here we have the kinetic term of the quarks and the chiral covariant derivative. The covariant gauge covariant derivative. So quantum chromodynamics is a gauge theory, as non-abelian gauge theory, where is a SU3 gauge theory, where the quarks have three colors and then is invariant under SU3 gauge transformation, and the gauge fields are the gluon fields. So the covariant derivative includes a gluon field, and then here this is the gluon field strength tensor. So the quarks, quark carry colors, and they interact with each other by emitting gluons, where the gluon carry colors. And then it turns out that the quark carry colors, but the hadrons are all colorless. So for instance, the meson, which is formed by quark and antiquark, they have color times anticolor, which makes it colorless. And for instance, the baryons, which has three quarks, you have red, green, blue added together to become colorless. So yeah. So as I say, so the quark carry color, but the hadrons itself, when you look at them as a whole, they are all colorless. So now, an important evidence that quantum chromodynamics is the correct theory for strong interaction is the so-called asymptotic freedom. People in experiments have observed that when collision experiment, for example, the lepton hadron scattering experiment carried out at very high energy, they observed that when this high energy experiment is performed, they seem to be able to be interpreted as electron interacting separately with the quarks, as if these quarks are free. So this shows that the quantum chromodynamics becomes weaker and weaker when we are dealing with high energy or high energy scale experiments. So this is asymptotic freedom, and it was quickly realized that non-abelian gauge theory possesses the property of asymptotic freedom, which is due to this gluon loops that give a so-called anti-screening effect. So that asymptotic freedom give us a very good make the QCD very useful as a fundamental theory in describing high energy processes involving hadrons. Namely, the strong coupling constant alpha S becomes smaller and smaller at higher and higher Q square. So in that region, we can perform a perturbative expansion of the amplitude in powers of the strong coupling constant. And in that case, and in that case, we can compute observables perturbatively using elementary Feynman rules, as you have learned in the standard QFT lecture. On the other hand, the strong coupling constant increases when energy becomes smaller and smaller. For instance, at the scale where we observe hadrons as low energy particles, namely hadronic scale at Q is close to 1 GeV, the theory becomes totally non-perturbative. Therefore, perturbative expansion in standard quantum field theory doesn't work. Therefore, now we have the challenge. We have a fundamental theory known as quantum chromodynamics. It's based on quarks and gluons, but we are unable to compute the consequence of this theory at low energy, which we need to describe the properties of hadrons. Therefore, the major challenge is that how do we predict static and dynamical properties of hadron at low energies with control theory uncertainty? So it seems to be difficult to do it directly using QCD. And of course, people have a way to do so. So if we can't do the calculation perturbatively, then we just do it non-perturbatively. This is known as lattice QCD. So it's the basic concept is that you start from the path integral formalism by Feynman. Maybe you have learned that in the QFT course. And then you compute this path integral directly without doing any expansion on the Lagrangian. By discretizing the space and time. So you perform the numerical integration, this numerical integration directly by using Monte Carlo method with a supercomputer. So it's very computationally expensive. But the lattice QCD has been extremely successful in predicting some of the hadron properties, such as the mass of the hadron. So as you can see, many predictions of the hadron masses from lattice QCD agrees perfectly well with the experiment. So the many static properties of the hadrons can be perfectly described by lattice QCD. But the problem is that when we are dealing with hadron-hadron interaction, then using lattice QCD becomes very inconvenient because the degrees of freedom of a QCD are quarks and gluon. So for instance, each baryon has 3 quarks, so 2 baryons has 6 quarks, and then you are dealing with a many body problem. That will make the computation extremely expensive, and there will be a large noise and so on. So the so-called signal to noise ratio becomes very small, and then you are not getting reliable results, and there will be a lot of lattice uncertainties. So that actually bring us to a more basic question. When we are dealing with hadronic degrees of freedom, for instance, we want to study the interaction between neutron and protons or neutrons and pion, is it the easiest choice to choose quarks and gluons as our basic degrees of freedom, as in QCD. So maybe this is not the most convenient choice because we do not observe free quarks and gluons. Just like if you want to describe the motion of a ball going from point A to point B, you don't need to start from its atoms, although the balls consist of atoms, but you just need its macroscopic properties. So you can just take the ball as a point-like particle and just goes with classical dynamics. Therefore, it may be worthwhile to rethink what are the better degrees of freedom that we should choose, and what is the most convenient theory that consists of these more conveniently chosen degrees of freedom. So that led us to the second section, which is the concept of effective field theory. So as we mentioned before, our goal is to have an accurate description of hadron-hadron interaction, but our challenge is that QCD is non-perturbative, and then it's very difficult to apply a lattice QCD directly to predict a hadron-hadron interaction. Therefore, we need a new theory formalism, which has on the one hand has the finite predictive power, and second, since we know the fundamental theory of strong interaction is QCD, so this new theory has to be fully consistent with QCD, and at the same time it has to be less computationally expensive than lattice QCD, and also it should be straightforwardly applicable to multi-hadron system. So and also it cannot be simply a model because a model has uncontrolled theory uncertainty. Therefore, a breakthrough of in this area was possible since 1979, when Weinberg introduced the concept of effective field theory. So this sentences of him is worth reading out. So the basic concept is that Weinberg has a assumption or a guess that although each quantum field theory, for example, the quantum electrodynamics called QCD or electroweak theory, each of these quantum field theory has, of course, a lot of content, but quantum field theory itself, without being specific to a model, has no contents beyond analyticity, unitarity, cluster decomposition, and symmetry. So cluster decomposition here means two different events. For example, an experiment in Chicago and an experiment in Bonn cannot affect each other. So if that assumption is true, then one can come to the following conclusion. Namely, if one writes down the most general possible Lagrangian, including all terms consistent with assumed symmetry principle, and then calculate matrix element with this Lagrangian to any given order of perturbation theory, then the result will simply be the most general possible S matrix consistent with analyticity, perturbative unitarity, cluster decomposition, and the assumed symmetry principle. So what does it mean? It means the following. If you want to describe an interaction using a quantum field theory, what you can do is to just write down a field theory using the degrees of freedom that you want, that is most convenient to you. And then the second thing is that you want to fix the symmetry of the theory. So for example, you want the theory to be charge conjugation invariance, parity invariance, and it have some flavor invariance. And then with this symmetry of your choice, you want to write down all the possible terms in the Lagrangian that satisfy this symmetry. You want to write down as many terms as you can, and then that forms the most general Lagrangian. And then you calculate the scattering amplitude, for instance, using this most general Lagrangian. Then Weinberg suggests that this outcome of the calculation cannot be wrong, because it's simply the most the outcome of this calculation just give you the most general S matrix consistent with all the general concept of quantum field theory and require symmetry. But this seems to be a very general statement, but now the question is, how practical is this statement? In particular, you just heard I say that you have to write down all the terms consistent with the required symmetry. All here obviously means there can be infinitely many terms of such, and each term can carry an unknown coefficient. So you don't know these coefficients, so you have to fix them by matching to experiment. But you have infinitely many of them. That means you need to match to infinitely many experiments. So does it mean that such a theory has zero predictive power because you are too busy matching your coefficient with experiments and then you can predict nothing, right? And the concept that saved the situation is so-called power counting. It's saying that you have to identify an expansion parameter in the effective field theory, which is small, and then you arrange all the terms in the effective field theory in increasing power of such expansion parameter. So if such an expansion parameter can be identified, then for any given precision goal, you only need to retain a finite numbers of terms in the Lagrangian because all other terms are suppressed by the powers of this small expansion parameter. And then when you only have a finite terms in the Lagrangian, then you can fix the finite numbers of unknown coefficients using finite number of experiments or a first principle calculation. So once this finite number of coefficients are fixed, then all other things are predictions of the theory. Therefore, let me summarize the basic ingredients of an effective field theory. First, you need to choose the degrees of freedom that you like, and then you want to choose the symmetries of the effective field theory you want them to satisfy, and then you have to figure out the power counting rule to truncate the Lagrangian so that you only need a finite number of terms for a finite precision goal. So chiral perturbation theory, or Chi-PT in short, is exactly a low energy effective field theory of quantum chromodynamics. So therefore, to construct chiral perturbation theory, we need to first identify the degrees of freedom that we want, the symmetries of the QCD, and what's the power counting rule. So to do so, let's study the symmetries of the strong interaction, namely the symmetry of QCD. Symmetry is obviously a very important concept in physics. Symmetry, by definition, is the invariance of a system under certain operation. So this operation can be continuous or it can be discrete. So for instance, this sphere is rotationally symmetric. Namely, if you do a rotation, the sphere looks the same. While this X is symmetric under mirror reflection. So if it will reflect the figure with respect to this vertical line, it looks the same. So so the rotational symmetry is continuous because you can do an infinitesimal rotation. But reflection is a discrete symmetry because there's no things like infinitesimal reflection. You can only do it once, right? There's no a bit of reflection that doesn't exist. And then you might have learned in the QFD course that there's an important, very, very important theorem called the Noether's theorem, which states that for any continuous symmetry in the system, it corresponds to a conserved quantity. So for instance, if the system is invariant under time translation, then energy is conserved. If it's invariant under spatial translation, then the linear momentum is conserved. If it's invariant under rotation, then angular momentum is conserved, so on and so forth. And to give you a simple example how to understand this Noether's theorem, let us consider this picture. So you bring a very heavy stone up a hill. So that spends you an energy because you want to build up the potential energy of the stone. And that spends you an energy of mgh. Suppose the gravitational constant on Monday is G, and then on Tuesday you throw the stone down the hill, then its potential energy turns into kinetic energy of mg prime h. Suppose the gravitational constant on Tuesday is G prime. Now, if the gravity is not invariant over time, namely the gravitational constant G prime on Tuesday is not the same as G on Monday, then we will gain a net energy of m times G prime minus G times h. So energy would not be conserved. On the other hand, if gravity is constant, is invariant over time, then G equals to G prime, then there's no gain of net energy. So energy is conserved. So this is a simple example. Now, in mathematical terms, in quantum field theory, a symmetry corresponds to an invariant of the action under certain operation, and a symmetry corresponds to a conserved, will give rise to a conserved current. So this derivation can be found in any QFD textbook. If you take a scalar field as an example, if you do an infinitesimal change of the field, which keeps the Lagrangian invariant up to a total derivative. The total derivative is fine because we just need the action to be invariant, and the action is the space-time integral over the Lagrangian. So if the infinitesimal transformation leaves the Lagrangian invariant up to a derivative, then by using equation of motion, you can show that this definition of current, we call it a conserved current, is conserved, namely its total derivative is 0. Using this conserved current, one can define a so-called conserved charge, which is the spatial integration of its 0 component. You can show that this conserved charge Q, the time derivative of it is 0, namely is invariant over time. It's very simple because ddq equals to delta partial t j0, and then is equal to, using this conservation, it becomes a spatial derivative of the spatial component, but then it turns into a surface integral. But you take the surface to be infinity, and suppose the current fall quick enough at infinity, then the surface integral is 0. So now let's be more specific and consider the QCD Lagrangian. What are the symmetries of QCD? So there are exact symmetries and there are also approximate symmetry. Let's first talk about the exact symmetries. Of course, the QCD is invariant under C, charge conjugation, parity, and time reversal. Suppose that there is no QCD theta term, which is a mystery why it's so small, but we don't talk about the QCD theta term. And these are discrete symmetry because there's no infinitesimal charge conjugation or infinitesimal parity, so it doesn't exist. On the other hand, we also have continuous symmetry such as Lorentz symmetry. That includes time and spatial translation and rotation and Lorentz boost. And then we have a U1 symmetry and a gauge symmetry, SU3's color. Let's talk about this example. What is U1V symmetry? It states that if you do a global unitary transformation to all quark field, namely you introduce an extra phase to all the quark field, then the QCD is invariant under such transformation because, as you can see, the QCD Lagrangian is always QQ bar. So the phase from Q is cancelled by the phase from Q bar. So this is a continuous transformation which leaves the Lagrangian invariant. So in that case, we have a conserved current, which is defined as this, and it corresponds to a conserved charge, which is nothing but the so-called baryon number. So baryon number is a conserved quantity, and a baryon, every baryon has a baryon number of 1, every meson has a baryon number of 0. So this number is conserved during all the QCD interaction. For example, a proton collides with a neutron, doesn't give you 2 pi's because baryon number is not conserved in that case. Because the initial state you have 2 baryon number equals 2, and final state you have baryon number equals 0. That cannot happen. So these are the exact symmetries of QCD. And it's also is useful to study some approximate symmetry of QCD. For instance, this one known as the flavor symmetry. So in talking about QCD, we can choose the number of quarks that we want. For instance, if we restrict ourselves to up quark and down quark, which are the lightest quark, then this is the QCD Lagrangian, consists of only up and down quark and the gluon. So the M is the mass matrix of the quark. So you have MU and MD in general, they are not equal. So now let us consider this transformation SU2V. V stands for vector, which is also known as the isospin rotation. So now you group the up and down quark field into a doublet, UD doublet, and then you do a so-called special unitary transformation, namely is exponential of something, and then here is the generator, which is a special, so-called Pauli matrix. There are three Pauli matrix, so 0, 1, 1, 0, 0 minus I 0, and 1, 0, 0 minus 1. So these are the Pauli matrix divided by 2 are the generators of the SU2 elements. So now it turns out that if MU equals MD, namely the up and down quark masses are the same, then this SU2 rotation will leave the Lagrangian invariant, because this is a constant, this is a matrix proportional to unity, to the unit matrix. Therefore, the V dagger here and the V here will cancel each other, because by definitions, special unitary matrix means UU dagger equals U dagger U equals 1. But if mass of up quark and mass of down quarks are not equal, then this rotation will not leave the Lagrangian invariant. Now, there are consequences of the of the isospin symmetry, as we see that this is a continuous symmetry, so it corresponds to a conserved current, which is this current. We call it isospin current, and then it will correspond to a conserved set of quantum numbers known as the isospin quantum number I and I3. It's just like rotation, a rotational symmetry, which is SU2. So SU2, the isospin is also SU2, but on a flavor space. So as you can remember, rotational symmetry leads to the concept of spin, rotational quantum number J and J3, or J and MJ. So for any state, for instance, for a proton state, you can have spin up proton, you can have spin down proton. The two states are of the same mass. Here is the same. So if you have a representation of isospin multiplet, and they are all having the same mass, but now the isospin symmetry is not exact symmetry, but only approximate symmetry. Therefore, the members of an isomultiplet have a very similar mass, but not exactly the same. For instance, the pion triplets are a representation of the isospin. Forms a irreducible representation of the isospin. Is represented by I equals 1 and I3 equals to 0 or plus minus 1. And you can see that the pi 0 and pi plus minus have very similar mass. The same is to rho meson, and the same is to proton and neutron. So proton and neutron are isospin doublet, and the pions and rhos are isospin triplet, for instance. So we keep saying that isospin is a not exact symmetry. So there must be sources that breaks the isospin symmetry. So there are two major sources. One is the quark mass difference. So this is a strong isospin breaking. And then there's a quark charge difference, because up quark and down quark couples to photon differently. The charge of up quark is 2/3, the charge of down quark is minus 1/3. So this is electromagnetic isospin breaking. It's interesting to see if you look at the QC particle data group, that up quark and down quark actually have very different mass. So the down quark is 2 times more heavier than up quark. Then you may naturally ask this question, well, they are so different, and the isospin symmetry requires up quark mass equals down quark mass. Then since they are so different, then why is isospin still a good symmetry? And the reason is that it's not about the relative size between the up and down quark mass, it's about its absolute size. So the up and down quark mass is much smaller compared to a natural scale of QCD. We call it the QCD energy scale, which is roughly speaking the scale where the strong coupling constant just blows up, is around 300 MeV. So if you consider isospin breaking effect, it is mu minus md divided by something, because you want a massless expansion parameter. And the denominator, the natural choice of the denominator is this QCD energy scale. And since this ratio is much smaller than 1, so as well as the electromagnetic coupling constant, the fine structure constant 1/137 is much smaller than 1. Therefore, that makes the isospin breaking effect very small. So it's not about the relative size between the up and down quark, but its absolute size compared to the QCD energy scale. And then we can extend this concept of isospin to include 3 flavors, the up, down, and the strange. Now we can write down a similar Lagrangian with 3 quark flavor, and then we generalize the SU2 rotation to SU3 rotation, and then the generated lambda over 2, where lambda are the Gell-Mann matrices, which have 8 of them, and the first 3 are just the Pauli matrices, and the next 5 will involve a strange quark. So now in this SU3 version, if the up and down and strange quark mass are the same, then the QCD is invariant, and then we have a SU3 flavor symmetry. In the SU3 flavor symmetry, we have a corresponding conserved current, and we can form a irreducible representation of hadrons by using the isospin quantum number I and I3, and as well as an extra quantum number, which is the strangeness. So that leads to the observation of the so-called 8-fold way, first observed by Gell-Mann and Niemann, saying that the hadrons can be grouped into different representation, and the simplest representation consists of 8 of them. For instance, the lighter pseudoscalar meson octet can be grouped into can form a group of 8, and then they have different isospin numbers and the strangeness. And similarly, the fused lightest baryon form a group of 8. So these groups are irreducible representation of the SU3 symmetry. So now you may ask, how good is this SU3 symmetry? So just like isospin, it is an approximate symmetry, but this SU3 symmetry is actually a bit worse than isospin, because as you can see, the strange quark is much heavier than the up and down quark, and is not so small compared to the QCD energy scale. Therefore, SU3 is a less ideal symmetry than SU2, as you can see in the hadron spectrum. So this is the mass for the meson octet, and this is for the baryon octet, and you can see that they shows quite some difference. Well, this the mass difference in this pseudoscalar meson octets is actually shows a lot of difference, but this is not due to the fact that the SU3 symmetry is just useless, but it's due to the smallness of the absolute mass of these the pseudoscalar octet, as I will explain the reason. And you can see from the baryon octet that although there are still some mass difference, but the difference is not as severe as this one. So now we have introduced the ordinary flavor symmetry in the 2-flavor version and 3-flavor version, and we can further introduce the so-called chiral symmetry, which is a generalization of the flavor symmetry. To do that, we have to introduce the so-called left and right-handed quark, which is defined by the use of gamma 5. So 1 plus gamma 5 over 2 is a right-handed projection operator, and 1 minus gamma 5 over 2 is a left-handed projection operator. So with this, we define the psi right and psi left. And by doing so, we can write the QCD in terms of the left-handed and right-handed quark fields. And then you can see the terms that that involve only left to left and right to right. And then there are terms that that mix left and right-handed quark fields. In particular, we see that this mass term, this quark mass term, will mix the left and right-handed quark field. Now, the chiral rotation consists of rotating the left-handed quark fields and right-handed quark fields separately. So instead of a SUN, where n is the number of quark flavor that you want to introduce, you want to evolve, for example, n equals 2 for up and down, and n equals 3 for up-down strange. So now, instead of just SU2 or SU3, you introduce SU2R and SU2L, namely the right-handed quark fields rotates in one way, and then the left-handed quark field rotates in another way. They are independent. So if you do the independent rotation to left and right-handed quark field, then you see that this Lagrangian is not invariant unless the mass of the quarks are all 0, because these terms go away. Then you only have left and right and right. Then the R dagger R, right, L dagger L will cancel each other. Therefore, QCD possesses chiral symmetry only if all the quarks are assumed to be massless. And then if chiral symmetry is there, then there are corresponding conserved currents known as this right-handed currents and the left-handed currents. And then you can add them linearly to form the so-called vector currents and axial current. And the vector current is nothing but the conserved current of the ordinary flavor transformation that we mentioned just now, SU3 version, which is isospin, and SU2 version, which is isospin, and the SU3 version, which is less ideal. While the axial current is a new thing, which we haven't mentioned before. And then, of course, we can have an equivalent representation of chiral rotation. So just now we introduced the independent rotational parameter, theta R and theta L. We can linear combine them to form theta V and theta A. And then if you take theta A equals 0, namely theta R equals theta L, then we reduce to the ordinary flavor transformation that we mentioned before. While for theta A, someone may call it SUNA transformation, but that's not rigorous because the axial rotation does not form a group because it's not closed. So we can only talk about chiral symmetry group and also vector symmetry group, but we cannot talk about an axial group because that doesn't exist. So now we have mentioned theoretically that if we take all the quark masses to 0, then chiral symmetry is there in QCD. And now we want to go back to reality and ask the question: is chiral symmetry really an established symmetry in the nature, approximate symmetry, just like isospin? We may suspect that it may be true because the up quark and down quark, as we mentioned, is much smaller than lambda QCD. So we might take it as 0. But there are some puzzle if we assume that isospin is, if we assume chiral symmetry is there in the nature. There's some puzzle that is very challenging to explain. One of the puzzle is the so-called the absence of parity doubling. So parity doubling is the observation that if chiral symmetry holds, then for any hadron, there should be another hadron of degenerate mass, but with opposite parity, because we can form an axial charge, which is a conserved quantity. In quantum mechanics, conserved means it commutes with the Hamiltonian. So if we take a hadron state n and act on act it with this axial charge, then it should give you another hadron state, which has the same energy as n of the original hadrons. So parity doubling states that if chiral symmetry holds, then for any hadron, there should be another hadron with the same mass but with opposite parity. But in reality, we do not observe such degeneracy. Namely, for instance, if we take the nucleon, which is spin half and with positive parity, you see that is 939 MeV. But if you look everywhere in the particle data group to find the lightest baryon of the opposite parity and same spin, you find that the lightest one is 1500 MeV. It's not degenerate at all. So we seem to have not observed this parity doubling in nature. So what have happened? So of course, a possible resolution is that just now we assume that the axial charge acting on the hadron give you another single hadron, but that might not be true. How about if this state is not a single particle state, but two particle state, the original hadron plus another almost massless particle? If that's the case, then the two states, so N and QAN, will be degenerate because you just add another massless particle. But what does it mean? This means the QA acting on the vacuum does not annihilate the vacuum, but creates a massless particle, which is very funny. And what does it mean? What is the consequence by the fact that QA acting on on a vacuum does not annihilate the vacuum? That will mean that we have a degenerate vacuum. Why? Because if you take 0 to be the vacuum here means the state of lowest energy, and then no particles there's just nothing, so lowest energy. And then if you add this operator on the vacuum of exponential of QA with an arbitrary real parameter, then since the QA does not annihilate the vacuum, therefore this operator acting on the vacuum does not give you the original vacuum, but yet this new state will have exactly the same energy as the original vacuum because it is just creating a bunch of massless particles. So the vacuum plus massless particle just give you the same 0 energy, right? So if you define your vacuum as here, so that what does it mean? You have a degenerate set of vacuum. That means the vacuum that means you have a spontaneously broken symmetry. It's most easily visualized by this so-called Mexican head potential. So the original, if you stand from here, then you have a rotational symmetry. But this point actually is not the most stable point. The most stable point is somewhere here, or it can be any point here around this circle you like. But once you choose a vacuum, so vacuum here refers to the state of lowest energy, then you stand from here, then you look around, you find that the symmetry is not, you don't have a rotational symmetry anymore because you have chosen a particular direction. And the fact is that there is a set of degenerate vacuum because you just walk around this circle, you find that the state that all the positions around this circle have the same energy. So you have a degenerate set of vacuum. Therefore, the absence of parity doubling suggested that there is a degenerate set of vacuum in QCD, which in turn suggests that the chiral symmetry is spontaneously broken in the nature. So, which means even if we assume all the quarks are massless, but we only end up with explicit ordinary flavor symmetry because the chiral symmetry SUNR times SUNL is spontaneously broken to a to a subgroup, which is just the ordinary flavor symmetry. And there's a well-known theorem that any spontaneously broken continuous symmetry will give rise to spin zero massless boson known as the Nambu-Goldstone boson. And just now we have already mentioned that. So the quark, so this axial charge creates a massless boson. So that boson is just what we call the Nambu-Goldstone boson. So if you have a vacuum state, compared to a vacuum state plus a bunch of Nambu-Goldstone bosons, since all these Nambu-Goldstone bosons are massless, so they still have the same energy. That's why you have a degenerate set of vacuum. So now, do we observe such bosons in the nature? Yeah, if we look at the pseudoscalar meson octet, we'll find that these scalars are unnaturally light. It's much lighter than any other hadrons that we observe. For instance, in the up-down sector, the pions are so light, it's 140 MeV, compared to the next lightest meson consists only of up and down, namely the rho, which is 770 MeV. Therefore, we can identify this pseudoscalar meson as Nambu-Goldstone boson. But you may ask, just now you say that the Nambu-Goldstone boson must be massless, but why do these guys have mass? This is because the chiral symmetry is not just broken spontaneously, but also broken explicitly by the non-zero mass of the quarks. So now just go to some mathematics. If you write down the axial and vector current as defined as before, and then you'll find that the divergence of their currents are proportional to the masses. And you see that if the mass, all the quark masses are degenerate, then the vector current is conserved. But in order for the axial current to be conserved, you need not just the degenerate mass of quark, but the quark mass to be zero. So spontaneous symmetry breaking says that the axial charge does not annihilate the vacuum, but create a Nambu-Goldstone boson. This can be stated in terms of a matrix element of the axial current. The axial current will annihilate a Nambu-Goldstone boson, and so by Lorentz symmetry, this is the only way you can parameterize this matrix element. And then if you take the derivative of the axial current, which is proportional to the momentum, then you see that the momentum dotted to right-hand side will give you the mass square. So if the quark mass are, so I mean, if the quark masses are zero, then the Nambu-Goldstone boson will be massless, which means the right-hand side equals zero, and which means the total derivative of the axial current will be zero. So the fact that in the chiral limit here means the limit where all the quarks are massless, the total derivative of the axial current is zero is known as the partially conserved axial current. Now, we have mentioned before that the spontaneously broken chiral symmetry generates Nambu-Goldstone boson. And at the same time, the explicit broken chiral symmetry, namely the non-zero quark mass, gives masses to the Nambu-Goldstone boson. So now, we have mentioned that the derivative of the axial current will give something proportional to the square of the Nambu-Goldstone boson masses. But in the quark level, you see that the derivative of the axial current is proportional to the mass of the quark. So that gives you an interesting relation, namely the square of the Nambu-Goldstone mass is proportional to the quark mass. So the square of this is linear to the quark mass, and this relation is known as the Gell-Mann-Oaks-Renner relation, which we'll demonstrate again later explicitly when we construct the chiral Lagrangian. So this is the first property of the Nambu-Goldstone boson. The square of its mass is proportional to the quark mass. And the second is about its interaction. So now if we take the axial, if you take an arbitrary matrix element of the axial charge, axial current, namely the axial current interact with any hadronic initial and final state, then you'll find that it will consist of two diagrams. Either it interact directly with the rest of the hadron system, or it interacts by first the axial current fluctuates to a Nambu-Goldstone boson, and the Nambu-Goldstone boson interacts with the remaining hadron system. So now in the chiral limit, the Nambu-Goldstone boson is massless. So this line gives you a massless propagator, I over Q squared. And then if you take the derivative of the left-hand side, and then in the chiral limit, the derivative gives you 0. Therefore, the right-hand side is 0 by dotted to Q mu. And so this gives rise to this relation Q times R equals to F times T, where F here is something called, is a constant, which we call the decay constant, and we will explain later. And then if you take Q equals 0, namely the Nambu-Goldstone boson is of vanishing momentum, then since this guy equals 0, so T has to also be 0. So it means the interaction T here between the Nambu-Goldstone boson and the rest of the hadronic system will vanish if the Goldstone boson has vanishing momentum. So this is another very important properties of the Nambu-Goldstone boson. Namely, it does not, in the chiral limit, it does not interact at vanishing momentum. So just now we talked about a spontaneous symmetry breaking, spontaneous chiral symmetry breaking. But also at the same time, we mentioned there are also explicit chiral symmetry breaking induced by the mass of the quarks and other things. For instance, is coupling to photon and coupling to the weak bosons. So let us understand how this explicitly symmetry breaking terms can be introduced to the Lagrangian. So now we start with the n flavor massless QCD. So massless QCD, you only have this kinetic term. Kinetic term can be split into right-handed part and left-handed part plus the pure gluonic part. So there's no quark mass term. Therefore, this part will satisfy a global chiral symmetry times U1 symmetry, which is the baryon number symmetry. However, as we mentioned, the introduction of a quark mass term will break the chiral symmetry. So that is an explicitly symmetry breaking term. So now we want to study the so-called symmetry property of the symmetry breaking term. So what does it mean? So let's take a look at the quark mass term. It breaks the chiral symmetry, but it breaks the symmetry in the specific way. So what is this way? The way is the following. If you assume that the quark mass matrix would rotate as m goes to Rm's L dagger under the chiral rotation, of course, in reality, it doesn't rotate. But if you assume that it rotates in such way, then this term has, again, the chiral symmetry because the R dagger here cancel with the R here, the L dagger here cancel with the L here. So the quark mass term breaks the chiral symmetry in such a way that that symmetry would be restored if you assume certain transformation rule of the quark mass term. So this concept is known as the spurion. So you can take, so the spurion is an object that would break the symmetry in such a way that the symmetry would be restored if one assumes a certain transformation of such object. So the quark mass matrix is can be taken as a spurion. Namely, it would restore chiral symmetry if you assume that it transforms in this way. So it's not just the quark mass term that breaks the chiral symmetry. There are also other terms. For example, if the quark couple with photons, or if the quark couple with the W and Z boson, then those coupling terms will also break the chiral symmetry. And the question is now that can we also recast these symmetry breaking term as spurion, such that if you assume certain transformation rule of this gauge field, then under flavor rotation or under Chiral rotation, then the symmetry would be restored. The answer is of course yes. That we can do it in a general way. So, in addition to the massless QCD, we can introduce the so-called external source term, where the quark fields interact coupled with these general vector sources, which are right-handed vector sources, left-handed vector sources, and there's U1 vector sources, and also the scalar sources S and P. So now these terms, of course, all of these terms breaks chiral symmetry, but the symmetry would be restored in a specific way. So now, what is this way, or what is this rule of symmetry restoration? The rule is the following. The full Lagrangian, which includes the massless QCD and the external source term, would satisfy a local symmetry SUNR times SUNL times U1V. Just now, the symmetry we mentioned before, the chiral symmetry and U1, are all global symmetry. Namely, the rotational parameter is independent of space-time. But here, we want to generalize the symmetry to a local symmetry, which of course doesn't exist. But this is an easy way to introduce a spurion. The rule is that this external source term would make the full Lagrangian satisfy a local SUNR times SUNL times SUNV symmetry if we assume that they transform in a specific way, namely if the right-handed and left-handed and the singlet vector sources transform as if they were gauge field under a local gauge transformation, and the scalar sources transform as R times L bar, as we mentioned just now, just like the quark mass term. So yeah, so this is the rule of to impose this external field. The external field breaks the chiral symmetry in a way such that if we assume they transform according to this rule, then the full Lagrangian would satisfy a local symmetry. So this is the way they break the chiral symmetry. So this set of spurion transformation rule is there in the ordinary QCD, and we want to impose the same set of rule in the chiral Lagrangian or in the effective field theory. So that is how we implement explicit symmetry breaking term into the QCD and also into the effective field theory. So let's now move to another topic, the so-called sigma model. So just now we talked about the spontaneous breaking of chiral symmetry will give rise to Nambu-Goldstone boson. But how do you realize that in the Lagrangian? So to introduce the concept of Nambu-Goldstone boson in the Lagrangian, we don't start with QCD because it's a bit more complicated. We start with a much simpler model called the sigma model, which is possibly the simplest possible model that gives you a good illustration of useful concept about spontaneous chiral symmetry. So this was introduced by Gell-Mann and Levy in 1960. So now the Lagrangian of the sigma model is the following. We have a two-flavor massless fermion field. So psi is you have two components in the psi field. They are fermions, and then it couples to some kind of bosonic degrees of freedom called sigma, and this sigma is a matrix, 2 times 2 matrix. So you have the fermion term, and you have the sigma term, sigma term, and then you have the coupling term between the fermions and the sigma. So now, This Lagrangian would satisfy a chiral symmetry SU2 left times SU2 right chiral symmetry if the right-handed and left-handed fermion field transform as this way, and then a sigma field transform as R sigma L dagger. Of course, so this will make this term chirally symmetric, and then by itself is chirally symmetric, and then this term is chirally symmetric. So now, So now, we have purposely chosen the sign of this term to be plus, because that would introduce a Mexican head-like potential, because these two terms add together give you the negative of the potential of the sigma, and you see that sigma equals 0 is not a vacuum because it has a high energy, but you want to go to some places lower, which say this. So this true vacuum will satisfy trace of sigma dagger sigma equals to 2v squared. That means the expectation value of the sigma is not 0. So these two terms together give rise to a spontaneously broken symmetry. Namely, the expectation value of sigma at the true vacuum should not be 0, but some non-zero constant. So knowing this, we can now parameterize the sigma field. So we can write it. We introduce two different ways of parameterizing the sigma field. One is called a linear parameterization. So we first isolate this constant, and then the rest are dynamical fields. So we call it the small sigma and the pi. So the small sigma and the pi's are dynamical fields. When they are 0, it goes back to the big sigma goes back to its expectation value, which is the v. So now in terms of this parameterization, you can plug it into in the original Lagrangian, and you get a new form of the sigma model. And you find that in terms of this new bosonic field, you observe that the small sigma is a massive boson because you have a mass term, but the pi is a massless boson because there is no pion mass term. And then also the originally massless psi has gained a mass, so the fermion also become massive. So now since the fermion acquires mass, so the chiral symmetry is explicitly broken. So from SU2R times SU2L to the vector part, because the doublet have the same mass. So the vector, so the ordinary flavor symmetry is still obey. So by the same time, you see that there's massless pion, 3 of them. So, and these pions are nothing but the Nambu-Golson boson generated by the spontaneously broken chiral symmetry, SU2 chiral symmetry. Okay. Now there's one thing very interesting. So from this slide to this slide, we have done nothing but just to adopt a particular parameterization of the big sigma. So we are just rewriting sigma in terms of something else, right? So how come in the original Lagrangian, there is a chiral symmetry, but just after re-expressing sigma by something else, the chiral symmetry is gone. Doesn't make sense, right? So a simple parameterization of sigma actually it cannot change the symmetry of the Lagrangian. So what actually happened is that the chiral symmetry is not gone, but it's just hidden because it's not explicit. Because in the original Lagrangian, the big sigma transform very simple in a simple way. R times sigma times L dagger is a simple way. So it's very explicitly that the chiral symmetry is preserved. On the other hand, when you reparameterize the big sigma into small sigma and pi, there is a non-trivial transformation of the small sigma and pi in terms of the chiral rotation. But that transformation rule is so complicated such that it's not obvious that this Lagrangian in terms of small sigma and pi is chirally symmetric. But in fact, it is still chirally symmetric if you can figure out the more complicated transformation rule of the small sigma and pi. Therefore, the spontaneous symmetry breaking does not mean the symmetry is gone. It's just hidden because the transformation rules in terms of the new field will be very complicated. So you can't see the symmetry at first sight. But if you repack everything back into sigma, then the symmetry becomes explicit again. Right. So one can imagine there's another way to reparameterize the big sigma such that we can introduce the massless Nambu-Goldstone boson, but at the same time, the chiral symmetry still remains explicit. And one of the ways is the so-called exponential parameterization of the big sigma, namely you parameterize the sigma as V plus small sigma times a unitary matrix U, and the U is exponential of something which involves this pi, which is our Nambu-Goldstone boson, divided by a V. And then we now define the chiral transformation rule of this U to be the same as the sigma, namely R times L dagger, while the small sigma is invariant under chiral transformation. So you plug this parameterization into the original sigma model, you see the following. You see again that the small sigma is massless. And then, and then you see the Nambu-Goldstone boson term in terms of the U matrix. And then you see the fermion term coupling with the U. And in this form, you can easily find that the chiral symmetry is still explicit because the U goes as U L dagger. So this term is obviously chiral invariant because the R here cancel with R dagger here. L dagger cancel with L here, and same for this term. And then this term is obviously also chirally symmetric because you have a trace. So the R can move there. So the R and R dagger cancel each other. So in this way of parameterizing the big sigma, you see that the chiral symmetry remains explicit, although you have introduced the Nambu-Goldstone boson pi here. This is called a nonlinear parameterization of the Nambu-Goldstone boson because it involves the exponential. Therefore, to obtain the kinetic terms and the interaction terms of the Nambu-Goldstone boson, you have to expand the exponential into powers of the boson fields. And then you may ask that we have introduced two different ways to parameterize the big sigma. Are they equivalent? So now in the linear way, we parameterize the small sigma and the pi as this way. So the subscript L means linear. And in the exponential parameterization, they are parameterized like this. But if you expand the U, then you see that this expansion. So when you do the matching, you see that the linear parameterization is equal to the exponential parameterization plus something else. This something else involves the product of multiple fields. And then when we have such matching, namely a field is equal to another field plus some other term which involve products of multiple fields, then we can conclude that the field A and field B are actually representing the same physical state, because when we use a quantum field theory to calculate, for instance, scattering processes, we are only interested in the final state that are well separated. And when they are well separated, we are only interested in the single particle singularities. And so this term and this term will have the same single particle singularity because the term which involves the product of field does not contribute when in the asymptotic state, when the particles are well separated. So this is a so-called representation independence theorem, namely, if you have field A equals to field B plus something, where the something equals a product of field, then field A and field B represent the same particle. So this is the theorem which was proven by Haag in 1958. So this means that the linear and exponential parameterization of the big sigma, in fact, they are equivalent, as we can show by computing some observables. For instance, you can compute the pi to pi scattering using the two representation. In both representation, you have to compute two diagrams. First, you have the direct interaction, and also you have interaction by exchanging a small sigma. So in their linear parameterization, you find that both Feynman diagrams give you a large result, but when you add the two Feynman diagrams, they largely cancel and give you a total result which is suppressed by the small momentum of the pions. So this means in the linear parameterization of the sigma, you cannot simply disregard the heavy boson sigma because it gives you a large contribution which has to cancel with the contact interaction with the pions to get a suppressed result. On the other hand, if you start with the exponential representation, then you find that the things are simpler because the contact interaction between the pions give you a momentum suppressed result. Whereas the terms which involve the exchange of the sigma will give you an even more suppressed result, so which is q to the power 4. Therefore, you can actually disregard this term when you're only interested at a precision up to q squared. So you find that this linear and exponential representation actually give you the same result for the pi scattering amplitude, but that you obtain the final result by with different degrees of difficulty. In the linear representation, you have to compute both diagrams, but in the exponential representation, the second diagram is by itself suppressed. Therefore, in the second representation, namely the exponential representation, you can actually disregard the sigma in the Lagrangian if you are only interested in the interaction of the Nambu-Goldstone boson. So this is the power of the nonlinear representation of the Nambu-Goldstone boson, that its coupling or its interaction is automatically suppressed by the small momentum of the Nambu-Goldstone boson. Okay. So just now we have already mentioned spontaneous symmetry breaking and then the explicit symmetry breaking, and introduced the way how one could parameterize the Nambu-Goldstone boson, namely the exponential parameterization. So after doing so, we can now introduce the ingredients that we should use to build up our effective field theory of QCD, namely the chiral perturbation theory. So we recall at the previous section that the basic ingredients of the effective field theory are of three kinds. First, you need to choose the degrees of freedom that you want, which are the hadrons. And then the symmetry of the effective field theory, which is just the symmetry of the QCD. So the discrete symmetries are CPT, Lorentz, and then the continuous symmetry are Lorentz symmetry, and then the U1 V symmetry, and also there are approximate symmetry, namely the SU2V or SU3V, and more generally the chiral symmetry, which has to be spontaneously broken into the flavor symmetry, ordinary flavor symmetry. Meanwhile, we do not need to consider the color gauge symmetry because all the hadrons are colorless, so it doesn't transform under the color gauge symmetry. And finally, we need to impose a power counting rule such that we can arrange the chiral Lagrangian in terms of increasing power of a certain expansion parameter and truncate the chiral Lagrangian at any precision goal that we want. So now the degrees of freedom of two flavor theory, namely we have up and down quarks. Then when we want to choose only the lightest meson and the baryon. So lightest meson are the pions. So we have 3 pions and 2 baryons, namely the protons and neutrons. But if we want a 3 flavor theory which involve up, down, and strange, then we will include the lightest meson octet, which is the pi, k, and the eta, and also the lightest baryon octet, which is proton, neutron, sigma, C, and lambda. So here, we as an illustration, let us first consider only the Nambu-Goldstone boson, namely the pi's and the k's and the eta in a 3 flavor theory. So we start by constructing an effective field theory consists only of the Nambu-Goldstone boson, 3 flavor ones. So we have 8 of them. Now, learning from the sigma model, we want to have an exponential representation of the Nambu-Goldstone boson. So we have exponential of this phi. Phi is a matrix which is a contraction between the small phi A and the Gell-Mann matrix, and F0 is a parameter to be determined later. And the phi A can be identified to the meson octet. So the pi plus pi minus and pi 3 and k plus minus and the k0 and the k0 bar and the eta 8. Well, the pi 3 and eta 8 are rigorously speaking not the physical pi 0 and eta, but they are related to the pi 0 and eta, which we'll explain later. And next, we consider the symmetry. So for the discrete symmetry, CP and T, we need to know the transformation of the matrix U under CP and T. And then the chiral symmetry, the SU3R and SU3L. So as we mentioned before in the sigma, so this is not there. So the U, following our experience in the sigma model, should transform as R times U times L dagger, while in the U1V transformation, it doesn't transform because this transformation is related to the baryon number, and the meson doesn't have a baryon number, so it doesn't transform. We have mentioned also that we need to include the explicitly symmetry breaking term, namely the quark mass term and also the vector external sources. So this can be introduced to the chiral Lagrangian again by assuming that the chiral Lagrangian would satisfy a local chiral symmetry if we introduce the external sources and the external sources transform in such a way that we defined in the previous section. So these external fields can be introduced in 2 ways at the leading chiral Lagrangian. First is through the so-called chiral covariant derivative. So we generalize the ordinary derivative to the U into covariant derivative by introduce the left-handed and right-handed external sources. So if we assume the transformation rule that we introduced before for the RU and LU, RMu and LMu, then under a local chiral symmetry, the chiral covariant derivative of U will transform just like U itself. So the R at the left and the L dagger at the right. On the other hand, the scalar and pseudoscalar sources can be introduced by introducing a quantity called chi, which involve a new constant of dimension mass, and the chi has to transform as R times L dagger. So just an example, if we consider QCD and nothing else, then the only symmetry breaking term is the mass, and it is a quark mass, and there's nothing else. So that will mean the RMu and LMu will be equal to 0, and only the scalar source is non-zero, and the chi is related to the quark mass matrix. So now, yeah, so this by introducing the covariant derivative to the U and the scalar source, we can put the symmetry breaking terms into our Chiral Lagrangian. And finally, the third ingredient of the effective field theory, which is the power counting rule. So we need to identify some small quantity in the theory that we can use to expand the Lagrangian. So just now we have mentioned an interesting property of the Nambu-Goldstone boson, namely, it does not interact at zero momentum. So if we are considering only the scattering processes between Nambu-Goldstone boson of very small momentum, the soft Nambu-Goldstone boson, then that small momentum itself can be taken as an expansion parameter. So we denote the small Nambu-Goldstone momentum parameter momentum as generically as P. Therefore, P can be taken as an expansion parameter. So we know that in the space-time coordinate, the momentum is related to the derivative. Therefore, the derivative, any derivative of mu of U will count as one order of the small momentum. So the d mu is count as 1 power of P. And then of course the mass of Nambu-Goldstone boson is the zero component of its momentum. Therefore, the mass of the Goldstone boson should also count as first order in P. But just now we have mentioned before that the square of the mass of the Nambu-Goldstone is linear to the quark mass. So if the mass of the boson counts as P, that means the quark mass, which is square of the Goldstone mass, should count as P2, P squared. Therefore, this scalar source should count as P squared. So now this is the simple rule. The derivative counts as P, the scalar source counts as P squared. So we can arrange, we can arrange the effective Lagrangian by counting the number of derivatives and counting the number of powers of the scalar source. And then we can arrange it into P squared, P4, and P6, and so on for the pure Masonic Chiral Lagrangian. So let's see how this is done. So to proceed, now we will construct a leading order Chiral perturbation theory in the meson sector. Namely, it consists only of the Nambu-Goldstone boson and nothing else. So now we want to write down the Chiral Lagrangian. All the terms in the Lagrangian consist of U is covariant derivative and chi, which is explicitly chiral symmetric and is non-trivial. So you will find that the lowest order Lagrangian that you can write out is of OP2. Namely, it either consists of 2 derivatives or 1 powers of chi. You may ask, how about U bar, U dagger U, and trace? Well, you need a trace because U is a matrix. So you want a scalar Lagrangian. But U dagger U equals 1 because U is a unitary matrix. So trace of it give you a constant. So the constant is of no use is in quantum field theory because you need something which has the field dependence. Therefore, the non-constant terms in the Chiral Lagrangian starts from OP2. So you either have a term with 2 derivatives or 1 powers of chi. So there are only 2 terms you can write down. So now, In pure QCD, namely you only have the quark mass term as a chiral breaking source, you find that the covariant derivative will just reduce to the ordinary derivative. And in that case, the term A will preserve chiral symmetry, and only the term B will break chiral symmetry because the chi has to be later identified to the quark mass, which actually doesn't transform. So the term B will break the chiral symmetry. Therefore, the term A, so only the term B will give rise to the mass of the Nambu-Goldstone boson because it breaks the chiral symmetry. So now to make use of this Lagrangian and to obtain the kinetic term, mass term, and interaction term of the Nambu-Goldstone boson, we have to expand the matrix U. So let's first study the masses. If we expand the U to second powers of the Nambu-Goldstone boson, then you get terms like this. We have a constant, and then you have the kinetic terms of the Nambu-Goldstone boson, and then you also have quadratic terms of the Nambu-Goldstone bosons. So these quadratic terms give rise to the masses. And in particular, you find an interesting thing that usually you have ordinary free Lagrangian of a scalar is something like half derivative of phi square minus half m square and phi square. But now you have several fields, so you should have so if they are all the fields are independent, you should have something like half psi half derivative of mu phi a square minus half ma square times phi a square. But now if you really expand the Lagrangian, you find that here there's an interference term between pi 3 and eta 8. Namely, there's a term proportional to pi 3 times eta 8. So this means pi 3 and eta 8 themselves are not actual eigenstate of masses because the mass matrix is not diagonal. Therefore, you need to do a rediagonalization to make the mass matrix diagonal, and that introduce the physical state pi 0 and eta 0. So after you perform this rediagonalization, you find the following masses of the Nambu-Goldstone boson. And you can see here, so the m hat is the average mass between the up and down quark, and the epsilon is the difference between down and up quark divided by its sum. So you indeed find that the square of all these Nambu-Goldstone bosons are proportional to the linear term of this quark masses. So this is what we have predicted before. And one interesting thing is that this term in the pi 0 and this term in the eta 0 comes from the rediagonalization of the pi 3 and eta 8. However, as you can see, these terms are actually suppressed by the average up-down quark mass divided by the strange quark mass, which is very small, 10 to negative 2. Therefore, in most practical cases, you can actually discard this term. So you can assume that there's no mixing between pi 3 and eta and take them directly as the physical state pi 0 and eta. And yeah, so these are two properties. And the third property is the so-called Gell-Mann-Okubo relation. So if you take the isospin limit, mu equals to md, then you will find that you can predict the mass of the eta by knowing the mass of the kaon and mass of the pion. So if you just now in the previous slides we have the table of the actual masses of the Nambu-Goldstone boson. If you plug them in to the right hand side, then you see the mass of the eta is quite well reproduced, up to 6-7% difference. So this is a leading prediction, the prediction of the leading order chiral Lagrangian, which already agrees pretty well with the experiment. And next, we can study the vector and axial currents. These are conserved current of the chiral symmetry. So in the three flavor, in terms of the quark field, the chiral currents are defined like this, which you can see before. And then the question is how to obtain this conserved current from the Lagrangian with external sources. So in fact, one can obtain these currents by taking derivative of the Lagrangian with respect to external source. For example, you can easily see that if you take derivative with respect to the right-handed external source, then you obtain the right-handed chiral current. If you take the derivative with respect to the left-handed external source, then you get the left-handed chiral current. So we can impose the same rule to the effective field theory Lagrangian, namely, these chiral currents in terms of hadronic degrees of freedom can be obtained again by taking derivative of the chiral Lagrangian with respect to the external source. So in the leading chiral Lagrangian, the external source appears in the covariant derivative. So if you take without going through the derivation, you can show that if you take such derivative, you get the leading order prediction of the hadronic currents from the chiral Lagrangian. So the left-handed currents are in terms of this trace of U and partial mu U dagger, and the right-handed current is similar. And then you can combine them into vector and axial currents, right? Which is plus give you the vector current and minus give you the axial current. So one thing to study using this hadronic form of the hadronic form of the conserved current is the so-called partially conserved axial current we have mentioned in the previous section. So if you expand the axial current to the leading powers of the Nabu-Boson boson field, then you get this form, which after taking the matrix element with respect to a single Nabu-Boson state will give you the same relation which we have introduced with the constant F0. So constant F0 is the constant that we introduced in the exponential of the U. So this F0 is called the decay constant of the Nabu-Boson boson in the chiral limit. So why it's called a decay constant is because if you consider some leptonic decay of the Nabu-Boson boson, for instance, the decay of the charged pion to muon plus muon neutrino, then we see what happened is that pion fluctuates to a W boson, which then decays to a lepton pair. And this fluctuation matrix element is exactly this guy because the W boson couples to an axial current. So the strength of this fluctuation is controlled by the F0 here. Therefore, the F0, that's why the F0 is called a decay constant, because it will determine the strength of the leptonic decays of the Nabu-Boson boson. And therefore, you can determine the F0 by experimental value of the strength of this decay. So an F pi here is like 92 MeV. So yeah, so just now we used the leading order chiral Lagrangian to study the masses and the leptonic decay of the Nabu-Boson boson. And let's do something even more complicated, which is the meson-meson scattering. So in the meson-meson scattering, you need to expand the chiral Lagrangian. So this chiral Lagrangian and collect the power and collect the terms in the chiral Lagrangian involving more fields of the bosons. So to study the 2-to-2 scattering, you need to retain the term which contains 4 powers of the Nambu-Boson boson, which are these terms. So these terms all have 4 powers of phi. So then you can write down a bunch of Feynman rules involving coming from these terms. So let's take a few examples. We study the Feynman rules that involve only the scattering between pions, from pion to pion. So there are 3 different independent Feynman rules. So pi plus pi minus to pi 0 or pi plus pi minus to pi plus pi minus, or pi 0 to pi 0. So this can be done. So these Feynman rules are written down by assuming isospin symmetry. So mu equals md to simplify the expression, so that we can just write down one single m pi instead of m pi plus, m pi minus, and so on. Yeah. Now, using these Feynman rules, we can study, for instance, the scattering length of the pi scattering. So we study pi scattering. So we can parameterize the scattering amplitude into the so-called isospin scattering amplitude, because the scattering of the S matrix can be expressed as 1 plus the T matrix, and then if you assume isospin symmetry, then the initial then the isospin must be conserved during the scattering process. So so if we start with 2 pions and we group the 2 pion into state of definite isospin, then this isospin must be conserved before and after the scattering. Therefore, the I here in the initial state must be the same as the I here in the final state. And thus we can parameterize the scattering amplitude as Ti. Yeah, where I can be equal to 1, 0, 1, and 2, because one pion has isospin 1. So 1 times 1 in group theory will give you 0 or 1 or 2. So now you may have learned in the 2-to-2 scattering, it's very convenient to introduce the so-called Mandelstam variable. The S variable, describe the S channel scattering, and the T variable will characterize the T channel scattering, and then the U parameter will parameterize the U scattering. And then they satisfy S plus U plus T equals to the sum of the square of all 4 particles in the initial and final state. In this case, 4m pi squared. So now, without going to more detail, you can actually prove, and I encourage you to prove by yourself, that the different isospin scattering amplitude can all be parameterized using a single amplitude. This is based on isospin plus crossing symmetry. So this single amplitude is the pi plus pi minus goes to pi 0 scattering. So it says that by this T and the exchange STU and UTS and so on, so all the isospin matrix, all the isospin amplitudes of the pi scattering can be expressed as the single amplitude T of different arrangement of the Mandelstam variable. So now, the pi plus pi minus to pi 0 can be computed using the Feynman rules, just nothing but this one, this Feynman rule. So with this single Feynman rule, you can obtain all the isospin amplitude. And with all the isospin amplitudes, you can actually compute something called the S-wave scattering length. The S-wave scattering length is just proportional to amplitude, where you have two pions coming with 0 momentum. So the S is just equal to S equals to m pi plus m pi square, and equals to 4m pi square, right? So in leading order Chiral perturbation theory, you can predict the S-wave scattering length with different isospin channel. So you can predict that in the isospin channel 1, there's no scattering length, and then so it doesn't scatter. It doesn't scatter at so the pi doesn't scatter at zero momentum, and then the scattering length of the isospin 0 and 2 channel are also predicted. And these actually can be contrasted with experimental result. For instance, the scattering length can be extracted from experiment by considering the an atom formed by a pi plus and pi minus. So, or even if you consider a kaon decay to 3 pion, and then the 3 pions at the final state will rescatter each other, which will affect the pion invariant mass in the k to 3 pi final states. And through the rescattering processes, you can determine the scattering length of the pi. So I won't quote the numbers, but you find that the leading order Chiral Lagrangian Chiral perturbation theory actually give a pretty good predictions of the experimental results of this pi scattering length. Just now we talk about some consequences by applying the leading order Chiral Lagrangian, which is OP2. So in the next few slides, without going to any detail, let me talk about what will happen if we want to increase our precision to include not just a leading order prediction. So just now we applied the leading Chiral Lagrangian to 3 level, but how about if we apply it to 1 loop level? Then what will be the power of the outcome? So we can count the power of the 1 loop by taking by this. So you know that all these vertices is coming from the OP2 Lagrangian, so they all scale as OP2 P2, and each of the propagators scale as 1 over P squared. So there's 2 propagators, so it's 1 over P4. And then finally, you have an integration over the loop momentum, which gives you P to the power 4. So if you multiply all of that, you'll find that a 1 loop diagram induced by the OP2 Lagrangian will be proportional to the P4. So so this gives us a general rule. If you apply the Chiral Lagrangian at OP2 to 1 loop, the outcome will be OP4. And how much is OP4 is supposed to be suppressed with respect to OP2? So it is suppressed by the following. So we have two extra powers of P squared in the numerator, but you have something in the denominator, which is another energy scale. And then it turns out that a natural energy scale in loop correction that's come out will be something like 4 pi times F0, which is about 1 GeV or 1.2 GeV. Therefore, the suppression of OP4 with respect to OP2 will be proportional to something like P squared over lambda chi squared. Lambda chi is what we call the chiral symmetry breaking scale. Therefore, this P over lambda chi will be that small parameter we use as an expansion parameter in the chiral perturbation theory calculation. So we just mentioned that applying OP2 to 1 loop gives you OP4, but that's 1 loop result. But you can, at the same time, you can also write down 3-level Lagrangian, which is by itself OP4. And that Lagrangian consists of much more terms than the leading order Lagrangian. It has, you see so many terms, and it was first written down by Gasser and Lloyd Weiler. And then it turns out that you need both the one loop from OP2 and the tree level from OP4 because when you do loop integration using the OP2 Lagrangian, you will get ultraviolet divergences. And the ultraviolet divergences have to be absorbed into these low energy constants from the OP4 Lagrangian at tree level. So for each of these low energy constant or LEC, you have to separate it into two pieces, the bare piece and the renormalized piece. The bare piece has to cancel the ultraviolet divergence from the one loop induced by OP2. And the renormalized piece is something you determine by experiment. And that is a very complicated program. And as you can see, if you increase the number of P square, you get more and more terms in the tree level Chiral Lagrangian. So in fact, at OP4, you already get so many of them. So 10 L's and 2 H. So you have 12 of them. In fact, when you go to OP6, the OP6 tree level Lagrangian for 2 flavor will give you something like 50 parameters. So you get more and more parameters, which you need to fit to more and more experiment. So the Chiral perturbation theory becomes less and less predictive when you go to higher and higher P square, because you have to fit to more and more experiments. So you can predict less and less things. Okay, finally, I think I have spent all my 2 hours. Maybe I can spend like 15 more minutes to talk about nucleons, right? Chi-PT with nucleons. So the nucleons are not something which is generated by chiral symmetry breaking. It is there, even there's no. Its existence is nothing to do with chiral symmetry breaking. So it's called a matter field. So the thing is that to put the matter field into chiral Lagrangian, again, we want to study how it transforms under chiral symmetry. So the only thing we know that it transforms under the good symmetry, namely the U1 times SU2. Here we talk about two flavor theory, so that we only consider the nucleon doublet, namely proton and neutron. So we only know that under this good symmetry, it transform like e to the I minus theta under U1V and times a vector matrix V in under SU2. So, but there's a freedom to choose how it transforms under the full chiral symmetry. So, to determine what is the most convenient choice of transformation of the nucleon doublet under chiral symmetry, it's easy to learn. It's useful to learn again from the sigma model we introduced in section 6. So if we consider the sigma model in the nonlinear representation, you see that in this term, which involves the coupling between the fermion and the U, this term involves non-derivative couplings between the fermion and Nambu-Goldstone boson. There's no derivative here, but yet this term still satisfies the general relation we introduced before, that the Nambu-Goldstone boson does not interact at zero momentum, because this term will give rise to a so-called pseudo-scalar coupling. So psi times gamma 5, psi bar times gamma 5 times psi times a pi, something like that. But you know that if you look at the spinor, psi bar times gamma 5 times psi will be 0 if there is no momentum exchange. Therefore, still the Nambu-Goldstone boson does not interact with the fermion if it carries no momentum. But it would be beneficial if we can see explicitly the momentum suppression directly from the Lagrangian without the need to go to the spinor. Namely, is there a way to reformulate the fermion field such that all the interaction involved are derivative-like? So if it's derivative-like, then that is automatically momentum suppressed. And it's possible to do so by introducing a quantity which is the square root of the big U, which is called a small u. By introducing this quantity, we can study the transformation of the small u, which will involve a new matrix called K. The K is a non-trivial matrix, which is also unitary, but it is not a is a field-dependent matrix because it involves the number goes on field pi. And the only thing we know about the matrix K is that in the vector limit, namely the R when the theta R equals theta L, then it reduces to the matrix for the vector transformation. And then it turns out that if you redefine a fermion field like this, which involves the multiplication of U and U dagger into the left and right components, respectively, then this newly defined psi prime will transform simply like K times psi prime under the Chiral transformation. And then according to the representation independence theorem, since psi prime equals to psi times something else, where that something involves the product between psi and the number goes on. Therefore, the psi and psi prime are actually describing the same fermion doublet. And it turns out that if we express our theory in terms of the psi prime instead of psi, then we'll get that all the interaction terms between the fermion field and the number goes on boson are explicitly derivative-like. It either appears as this thing called the chiral covariant derivative, which involves this gamma mu. Gamma mu is something called a connection, which involves derivative of small mu, so small u. So the coupling to the pion is derivative-like. And the other term here involves another axial vector, which we call the field bind. This is a German term. Field means many, binds means leg. And this term is also derivative-like because it involves derivatives of the u. Therefore, in this newly defined, so the lesson we learned is that if we define the fermion field to transform like K times psi, then in this language, we can write the Lagrangian in a way that all the couplings are derivative-like. And in that case, the momentum suppression is more explicit. So, so now we can introduce the building blocks of the Chiral perturbation theory, which includes the fermion. So now we want a global symmetry, which is SU2R, SU2 left, and then the U1V. And then we also have a nucleon doublet, which transform as under this symmetry as n goes to K times n times this U1V transformation, which is just a phase transformation. So again, in order to incorporate the effect of explicitly symmetry breaking terms into the Lagrangian, we need to involve also the external field, external sources, R mu, L mu's, and the V mu S. So that, and then they are implemented in such a way that if we assume the external field transform in certain way, then the symmetry, the global symmetry becomes a local symmetry. So by that requirement, we can introduce the chiral covariant derivative of the nucleon that includes not only this connection term that we have seen just now, but also the external sources term, which transform just like, so the chiral covariant derivative of n transform just like the ordinary n. And then we also generalize the definition of the field bind to involve also the external sources term. At the same time, we can rewrite the spurion, the scalar sources, by multiplying them to U bar U, U dagger, and UU. And you see that all this definition is such that the transformation all depends on only a single matrix K and K dagger. So all the chiral building blocks has simple transformation which depends on K and K dagger. Therefore, it's easy to construct chirally symmetric Lagrangian based on these building blocks. So we quickly glance through the leading order chiral Lagrangian in terms of these blocks. So the pion Lagrangian, which we have introduced in the previous section, just now we have F0 over square over 4 times trace of U dagger U covariant derivative, and then with U chi dagger plus U dagger chi. But now we can rewrite it in terms of this field bind. So and the chi plus. So this Lagrangian is just exactly the same as we introduced in the previous section, just it looks a bit, just the appearance is a bit different because we do not use U, but use the field bind. On the other hand, in the nucleon sector, the leading order Lagrangian that we can write down, it turns out that it's not OP2, but OP, because in the nucleon sector, we can have one derivative, not just two derivatives, because the gamma mu will have one Lorentz index, so it can be contracted with the single derivative. Therefore, we have this term, these two terms, which are chiral invariant. Well, in fact, all of them are chiral invariant. Yeah, so we have these few terms which give you the kinetic and the mass term of the nucleons. And this term will give you an axial pseudo vector coupling or axial coupling between the nucleon and the number boson or boson, which are the pions. And the GA here is the axial coupling constant, which is matched to the experiment is something like 1.27. So let me just give a very quick application, introduce a very quick application of this Lagrangian in the nucleon sector, and we'll go to the summary. So just a few more slides. So in neutron beta decay, the neutron couple with the with the proton by emitting to W boson, and which then turns into electron and neutrino pair. So it involved the nucleon matrix element of the charged weak current, which can be written as the difference between the vector current and the axial current. So now, when we compute this process in chiral perturbation theory, there are actually two terms, two diagrams. First diagram is the weak current, the W boson couples directly with the proton and neutron. And second is that it first fluctuates into the pion, and then the pion couples to the nucleon. So this will involve different forms of the vector and axial current, because you see that the weak current has axial and vector component. So for this term, for this diagram, we need the pure nucleon contribution to the vector and axial component, while for this term, we need the pure pion contribution to the axial current, because the current goes to the W goes to the pion, and then the pion couples strongly to the nucleon. So in order to evaluate the second diagram, we need to the NN pi coupling, which can be obtained from this term by expanding the field bind to the first order in pion. So you can write down this particular Feynman rule. And then by doing so, you can write down the Feynman, the result of the Feynman diagram of this diagram and the first diagram, second diagram. So these first two terms come from the first diagram, and these terms come from the second diagram. As you can see, there is a pion propagator here. which adds to give you the final result. So these are the form factor. This gives rise to the form factor we call the F1 and the GA, and we call it G3 sometimes here. So from this result, we have actually derived two important relations. First is the so-called Goldberger-Tremann relation. This relation says that the axial coupling constant GA, which appears in the weak decay of the neutron to the proton, the beta decay, is actually equal to the strong interaction coupling between nucleons and a pion. So this is interesting because it turns out that the weak coupling constant is equal to a strong coupling constant. And this shows that the weak coupling constant, the weak decay process is induced by the pion, which first the nucleon couples strongly to a pion, and the pion decays weakly to the lepton pair. And second is, of course, the PCAC, partially conserved axial current. Namely, if you take the derivative of the axial current of the weak current, and then assume chiral limit, namely the Nambu-Goldstone boson is massless, then it will give 0. Yeah, so both the axial and the vector currents are conserved in the chiral limit. So this is PCAC. And finally, there's one more complication by applying the chiral perturbation theory involving nucleon. Namely, we have an issue in the power counting, which I just give a brief introduction, but not go into detail. So just now we mentioned that the power counting in chiral perturbation theory consists of some soft momentum divided by chiral breaking scale, and chiral breaking scale is about 1 GeV. So what is the typical soft momentum? Now, if we consider only the chiral perturbation theory of the Nambu-Goldstone boson, then in the two-flavor, typical soft momentum scale is the mass of pion, which is very small, so the convergence is pretty good. And in the three-flavor, we could have the so-called soft momentum as heavy as the kaon mass is around 500 MeV, still less than chiral breaking scale, but the convergence is much lower. But now the problem is when you have a theory involving the nucleons, then this momentum scale could be the nucleon as heavy as the nucleon mass, but the nucleon mass is 939 MeV, is almost the same as a chiral breaking scale. In that case, P divided by lambda chi is almost order of 1. So it looks like there's no convergence because the expansion parameter is 1. So it looks like the power counting breaks down. And the breakdown occurs when you are studying the loop diagram involving the nucleons, because in the loop diagram, you have to involve a propagator of the nucleon, and then this heavy mass scale nucleon mass will appear in the denominator in the propagator. But after loop integration, it could appear in the numerator. So now you have a heavy numerator, and you have a big numerator divided by lambda chi, and there is no convergence in the power. So this shows that a naive application of the chiral perturbation theory involving the nucleon will lead to a breakdown of chiral power counting. So there are a few ways prescription to restore the chiral power counting. So the first and the most easiest one is the so-called heavy baryon chiral perturbation theory, first formulated by Jenkins and Manohar. Namely, if you try to redefine the nucleon field such that you scale out the heavy mass term, and then the remaining nucleon field appears as a massless excitation, which carries a residual momentum very much smaller than the chiral breaking scale, so that Now the power counting is p residue divided by lambda chi, so it's good. And the other possible ways is the so-called infrared regularization or extended on-mass shell scheme, where you do not redefine the field, but in performing loop integral, you'll find that there are terms that breaks the power counting and the terms that obeys Chiral counting. And it turns out that the terms that break power counting are always polynomials. Therefore, you can adopt a subtraction scheme to subtract away these extra terms and retain only the terms that are behaving well in the Chiral power counting. So these are different ways to restore power counting in the existence of the nucleon or heavy barrier. So yeah, this comes to my summary. So we have explained why is it difficult to directly apply quantum chromodynamics to study hadron-hadron interactions, and therefore, to overcome this issue, we need to introduce a more practical computational method, and which is effective field theory, and then we introduce its ingredients, the degrees of freedom, the symmetries, and the power counting. And then we review the exact and approximate symmetries of QCD, especially the chiral symmetry. And we explain that how the chiral symmetry is explicitly and spontaneously broken. And the spontaneous broken of chiral symmetry will give rise to the Nambu-Goldstone boson. And using the sigma model, we illustrate how the Nambu-Goldstone boson can be parametrized in a nonlinear way, which makes the chiral symmetry remains explicit in the effective Lagrangian. With that, we constructed the leading order chiral Lagrangian, which is a chiral perturbation theory, which is an effective field theory of QCD based on a spontaneously broken chiral symmetry. And we have applied the leading order chiral Lagrangian at 3 levels to study some properties of the hadron, such as the Nambu-Goldstone boson masses, the pi-pi scattering, and the neutron beta decay. So as I mentioned at the beginning, this is a very superficial introduction of the theory, and I will strongly recommend you to refer to the resources, the textbook that I mentioned at the very beginning for more details of this subject. And anyone who are interested in working on hadron physics or nuclear physics are highly recommended to study to have an in-depth study of this subject, because, as I mentioned, it serves as the basis for such calculation. So yeah, so that's the end of my this short lecture. So thanks for listening.